We are just about at starting time, so I'm going to go ahead. And I'd like to introduce myself. My name is Denise Baim. I work for Host Telecom, and we are headquartered in the Czech Republic, and we create custom data infrastructure for cloud. We specialize in putting cloud OpenStack on bare metal, and we also have OpenStack tools that are based on OpenStack-based tools based on OpenStack. I love redundancy, apparently. For disaster recovery, data hosting, or data replication, and migration. So today, we're going to talk about cloud object storage and using different infrastructures underneath, as well as how to maintain the software on top to get the best performance. I will cover the initial architecture that was used when we had a major screw up and did everything wrong. You'll see all the stupid things that we did. And from that, we learned some great lessons on how you ought to do it. So that's what we'll do today. So we wanted to use OpenStack Swift from the beginning of creating object storage. We knew we wanted to be open source. I think maybe at the time, we weren't sure why that was necessarily the best idea, but it seemed like a great idea. And we wanted something that would allow us to scale easily when we hit a certain point, and we really weren't prepared for how much demand we would get with that service and how quickly we would max out our infrastructure. I'll cover the initial stuff that we built. And so we were flying by the seat of our pants, really. And we built a Swift solution, configured everything in the hardware underlying it. And we started off trying to build it with Swift documentation, which kind of ended up to be a problem because it wasn't, there just wasn't enough information there for us to develop from it. And so we started diving in to other Swift applications that had been built and using the code comments, which helped us to continue building our own solution. And so we had a successful launch, and we got some great response from our users. And we thought it was going to be super easy to scale and to use different hardware configurations. Sorry? It's right click. You got to select the screen again. Oh. Now I'm totally screwed. I hate PowerPoint.
You just hit F5 and go back into show, and it's the wheel, yeah?
That one.
The wheel, yeah. It's
yeah.
the wheel, man.
I just changed it.
It's the wheel, trust me.
It's the wheel. I'll trust him. So we got about a year down into it, and our data volume reached about a petabyte and a replication factor of 3. And the number of stored objects was approaching several billion. And our growth was about to kill us. We weren't getting high performance with Swift, and we really had to scramble. Users were really starting to get timed out. Disk space was full, so of course latency increased. And we were at a critical moment. We hadn't been able to define the underlying problem of why we were seeing all of these weird malfunctions. We didn't have monitoring enabled, and we couldn't pinpoint the slowdown. And we really started to question the viability of Swift, and we're starting to consider Ceph, even though we didn't have much experience with it either. Our servers were at capacity, and the drivers process and the network maxed out. And at about that point, the rats started to jump off the ship. Everybody, have you guys ever had the rats jump off your ship when everything got totally screwed up? I didn't do that. I'm out of here. So we, again, we had complete degradation in storage performance, and it turned out that all the changes we made to the proxy server had screwed up the cluster. So it just got better and better. We added several servers to expand the cluster. We saw some minor improvements in latency, but a huge slowdown in data replication, and again, we couldn't pinpoint the cause. When we increased replication speeds, data integrity was compromised, and we again saw an increase in timeouts, which obviously greatly inconvenienced our customers. We couldn't tell if the cluster had rebalanced, but when the Swift cluster was renewed, we saw a huge data loss and data inconsistency. And it took about 6 months to fix everything. We changed the software. Are you guys like, I would have known better than that? I would have had that figured out. Changed the software and the server architecture, and we eliminated all superfluous functionality to make sure that we had strong object storage performance. So we started the do-over. So you've seen how we royally really messed it up and where we ended up, and our SAT infrastructure fixes. And so now I'm going to talk about things that we did the next time around to create a much better solution. And we really started with analyzing the customer load profile and object storage resources and creating an IT infrastructure that would actually be able to scale. So we'll talk a little bit about Swift versus Ceph for object storage, different configurations, and maximizing the environment for Swift. So a lot of people in the industry say open solutions just don't work, but they do if you test them, and they do if you put some care into the code, and they also work really well when you don't test them in a production environment. So that was kind of a big one. And I think maybe smaller companies may be a bit more renegade about, hey, I think it works, send, ship it. So when you're defining your customer, you usually have one of two types, or at least you have two types of ways that they use data. The first type is static data on high-load applications, or scalable applications, like mobile applications, CSS, JSON, graphics, photos, animation, and Flash games. And the data storage requirements for static data are between a kilobyte to several megabytes. In general, users can access this data from storage, and Instagram is a good example of that. And the second type of data storage is archive data, and you'll see this more in healthcare institutions and businesses that have a lot of digitized data, like documents, and database backups of varying information are considered archive data. So we're going to take a closer look at the hardware involved in cloud storage and the basics about data read-write. Capacity and efficiency are really of primary importance here rather than speed. So here we're looking at a simple load executing triple replication. The proxy server receives the put query for the 3 data copies and creates 3 requests to the object server with 2 successful replications. And the object server returns a response of 200 to get to the client. Storage disk load and bandwidth increased times 3. And with the GET request, the load's proportional to the incoming request. I'm a paper girl, I know. I should have been from the 19th century. So IOPS and capacity. So we're going to take a different look, a closer look actually, at the efficiency and capacity of IOPS. Keeping in mind that productivity doesn't necessarily depend on disk capacity. Did we go to the next slide? I'm just like getting really happy about that. So wanting to avoid the risk of single points of failure, some providers will avoid using multiple disks to increase volume, sometimes preferring, let's say, a 2 terabyte in 2 unit server. So get that big fat server. Another option is JBOD, containing 44 disks at 10 terabytes each with an occupied space of 4 units. While you might worry about points of failure with that type of setup, we'll go over how to make that work. We'll also address maximizing IOPS on similar storage volumes. So the issue of cost efficiency is really serious, and when you look here, that is really an estimate, but it's a good probable estimate of the cost between these two types of solutions. So looking at that, you might want to keep that in mind when you're setting yourself up. And then coming back to volume and IOPS, we can calculate object storage availability. And obviously, greater volume means more data storage. And IOPS is really key to balancing data volume and required disks. We need enough to handle client traffic. And so now I'm going to talk a bit about cap theory very briefly before we start comparing Ceph and Swift. So basically, a distributed data store can't simultaneously provide availability, consistency, and partition tolerance. And you can get 2 out of 3. So a normal distributed system provides availability and consistency. And Ceph was really created for block storage and limited volumes. Then it was used for both object storage and for a clustered file system. And we know that Red Hat will tell us over and over again that Ceph is every bit as good and fast and wonderful as Swift. I don't know that I agree with that. Ceph's strength is maintaining data consistency. And when an object storage device fails or stops, the crush algorithm automatically starts the rebalancing process to redistribute data. Ooh, one spot. And you can see rebalancing is prioritized over client requests, so you can see slowdowns there and timeouts with Ceph. And Swift, on the other hand's major priority is client traffic, followed by asynchronous object writing and deletion. Then checking data consistency and data replication. So you can see pretty much, where those two projects are and what their priorities are. So keeping that cap theory in mind and hardware, we can look at optimizing object storage deployments. So Swift normal load. In Swift, processes fall into several types. And the first ones serve client traffic, second perform asynchronous writing and deleting of objects, and the third checks data consistency and, if necessary, it replicates data. Under high load, the Swift cluster performance on the hardware does take a bit of a hit. With most disks loaded to I/O, only 2 replications are written rather than 3, with the third delayed to the asynchronous queue line. With latency, you see a dip in software performance. When a server or disk fails, replication is interrupted, obviously, and data system consistency declines. And if you want to expand the cluster, you must add new servers to the ring and rebalance it. So the client traffic continues to process normally. If you just add a server and you don't rebalance, you get a pretty major decrease in IOPS and physical storage, and replication and consistency suffers. System restoration is really slow, and the speed of client traffic greatly decreases. Okay, so there's really no miracle cure, but there are methods to get better performance. First, you should really optimize the load on disk and create 2 tiers to do that for different types of customers, or at least the 2 types of way that they use data. When customers put high load on storage at different times, you might be tempted to put them on the same disks and think, oh, well, if they're using it at different times, then that's all going to work. But it really doesn't. So with disks performing client operations, IOPS are constrained around replication, and you do get a negative effect on data consistency. And another suggestion is bottleneck optimization. Am I in the right place? Yes. Oh. Don't laugh at me. And which means adding a cache system for IOPS, reading and writing. This is more important for the hot tier with higher read-write demands. And for writing, we use Enhance IO, placing cache on MVM disks. Sorry, I just got an email that covered my presentation. So as I pointed out earlier, a big problem with Swift is inaccessible disks. If the disks are in the server and you shut it down, you lose them. But you can solve the problem adding JBODs to another server. If we add dual-ported SAS disks, we can extend JBOD to 2 servers. And we can also switch them to other servers if you need to minimize downtime and preserve data integrity. And with that, I conclude and thank you. And I realize that was pretty brief, but we wanted to show you how we did it and how some things that hopefully you'll take into consideration before you find yourself swimming in a morass of data infrastructure no-worky. So, and again, we do invite you to test at Host Telecom if you like. And there we are. So does anybody have a question? Okay, thank you.